Okay, I think, okay. So I think we're up and running as far as the YouTube is concerned. Let me minimize that. And let me go back to the PowerPoint. Okay, so let me go back to what I was discussing earlier. So as I was saying earlier, let me go to my full screen mode here. The types of forces that are involved in chemical bonding are electrostatic, which means that these are attractive forces between charged particles of oppositely charged particles. And the example I'm pointing to here is that of hydrogen. We all know that each hydrogen atom consists of one proton and one electron. So in the case of two hydrogen atoms, you have a situation where you have two electrons between them and two protons between them. And there are different forces at work here. So basically, in the case of the positively charged particles, they will have repulsive forces between them like this. And the same is true for the negatively charged particles. However, when it comes to the particles of opposite charges, there will be forces of attraction between them. So you're going to have a force of attraction here, a force of attraction here, a force of attraction here, and here, right? So the stability of this molecule is dependent on whether or not the attractive forces are greater than the repulsive forces, right? And it turns out that in the case of the hydrogen molecule, that's the case. And that's why hydrogen is a stable molecule under normal conditions, right? Now, what we have down here is a different representation for the hydrogen molecule with one electron lost. So therefore, that changes things a bit. You'll only have repulsion or attraction, I should say, between the proton of one atom and the one electron here. And the same is true on this side. And as a result of that change, what you'll find is that the H2 plus ion is not stable. So you will not find the H2 plus ion existing under normal conditions, all right? So that's just one example. And we see similar forces at work when it comes to even more complex molecules. And basically what it comes down to is that if you have more or stronger attractive forces compared to repulsive forces, then the molecule or the structure will be stable, right? If the repulsive forces are greater than the attractive forces, then the structure will not be stable and therefore will more than likely react to form something more stable, all right? So that's basically a summary of how the electrostatic forces would result in a structure being either stable or unstable. Okay, so again, looking at the hydrogen molecule, as we said before, what you'll find is that there is a, what should I call it now? There is a bond distance between the two atoms for which the molecule will be stable, right? Now, if you somehow shorten that bond distance by bringing the atoms closer to each other, then what will happen is that the repulsive forces between the two nuclei will take over, right? And therefore, the system will become less and less stable as you force the atoms closer to each other. On the other hand, if you try to pull the atoms away from each other greater than the bond distance where it's stable, then there will be a force of attraction which would oppose the pulling of the atoms from each other, which again renders the atom more unstable as a result. And that is what is actually represented in this graph right here. So in this graph, you have the x-axis here, which is the distance between the two nuclei, and you have the y-axis, which represents the potential energy. This is the 0 point here, which represents, well, when no force of attraction is applied. And if you have, well, basically above the 0 point here, this represents a situation where the energy is used to separate the atoms, and below here is where the energy is used to compress the atoms or force the atoms closer to each other. Now, so as I said before, as you go from the minimum equilibrium position right here, all right, that's where the molecule is stable, and the bond distance at that point would be 74 picometers. Now, if you were to push the atoms closer to each other, as I said before, there would be some resistance to that because the nuclei which are positively charged, will repel each other. And therefore, what will happen is that the energy would increase, right? So basically, the energy would increase pretty much as you shorten the distance between the two nuclei. On the other hand, if you start pulling the atoms from each other, then basically what will happen is that there will be a resistance to that because, of course, there is an attraction between the shared electrons and the nuclei, and that will continue to increase. The energy will increase as you do that, and it will approach the 0 point here. And the 0 point here is basically reflective, actually, of the fact that this distance, or whatever the distance is, which requires the energy to be 0, at that point, the atoms will be so far from each other that they will have no influence on each other in terms of repulsive or attractive forces, all right? So this is basically showing you how the energy changes as the internuclear distance increases or decreases for the hydrogen atom. And as stated here, chemists or physicists can determine the energy required here to basically break apart the atom or the molecule to form the individual atoms, right? And that energy, in the case of hydrogen, has been determined to be equal to minus 436 kilojoules per mole, right? So that's the energy here below the 0 point. So what that means basically is that in order to break apart the molecule to form the separate atoms, you're going to need 436 kilojoules per mole of energy in order to do that. And that energy is called the bond dissociation energy. And we're going to talk about that in more detail shortly, all right? In fact, quantum mechanical calculations can then be used to develop theoretical models to delve into more deeply the actual behavior of the atoms in this particular setting, all right, or the molecule itself. And I need to say that because the idea behind this model here that is used to explain this graph right here is a model where the two atoms are considered to be spheres and they're connected by a bond which has a spring-like behavior. So if you think of two masses connected by a spring, that's a model that is used to explain the energy changes shown here. But of course, we now know that that model is insufficient to describe exactly what's happening. So therefore, quantum mechanical calculations has been used to revise and refine the model so that it can more accurately represent what is actually going on. But of course, we won't get into that deeper discussion in this chapter. So the next thing I want to talk about is the Lewis theory of chemical bonding. And basically what Lewis says is that the electrons, and in particular, the valence electrons, play a fundamental role in chemical bonding, all right? And basically what Lewis is suggesting is that when you have atoms combining to form molecules or ionic compounds, what they do is that they lose, gain, or share electrons in order to form these bonds. And in doing so, they tend to acquire the electron configuration of the nearest noble gas element in the periodic table to them, all right? So that's what Lewis came up with to explain chemical bonding, all right? And one can see that in several simple examples, such as the reaction between a metal and a non-metal. So as stated here, when metals and non-metals combine, what happens is that you have the valence electrons being transferred from the metal to the non-metal, and the result will be the formation of ionic bonds. And one can see this taking place in the reaction between sodium metal and chlorine. So the picture that you see on the screen here is basically showing you what happens when you have a vessel which has chlorine gas, and you add a small piece of sodium metal to it. All right, so basically the reaction that is taking place here is, hold on 1 minute, let me get my pen function ready here. Let me write it down here. So the reaction that is taking place here is a reaction between, oh shoot, I forgot to plug in my tablet. So let me do that now. Okay. All right, so the reaction that is taking place here is the reaction between sodium solid plus Cl2 gas to form, and of course the balances, we're going to need a 2 here, to form 2 NaCl solid, right? And as you can see, this reaction produces a lot of heat and light energy. So this reaction is very exothermic. And then once the reaction is completed and the heat subsides, then what you'll see below at the bottom of the flask will be crystals of sodium chloride, all right? So in the case of sodium chloride being formed, what you have are electrons being transferred from the sodium atom, which is the metal, to the chlorine atoms, which would be the nonmetal, to form sodium chloride. Now, in the case of covalent compounds or molecular compounds, you don't have the complete transfer of electrons from one atom to another. Instead, you have the sharing of electrons. And let me say that this only happens between nonmetals. It does not happen between a metal and a nonmetal, right? So in the case of covalent compounds, what you have basically are two nonmetals or more coming together, sharing electrons between them, and they end up with a covalent bond. Now, the covalent bond is a force of attraction between the shared electrons and the nuclei of the atom. So it's an electrostatic force, but not between ions, all right? It's between the nuclei and the shared electrons. Okay, so that's basically it as far as the difference between ionic bonds and covalent bonds, all right? So let me, oh, you have a question?
Have we done any, like, without the focus on covalent bonds and ionic bonds, have we done problems that have covalent bonds in them, or have we only done ionic bonds so far?
Well, the only problems that we did so far, when it came to naming molecular compounds which have covalent bonds. So that's basically all that we have done so far. We did the same thing for ionic compounds. I think we're going to see shortly some examples of covalent bonding, because that's what this chapter is based on. This chapter is just based on bonding. So we didn't actually get into it in any great detail in previous classes. All right?
Cool.
Okay, so let's talk about Lewis symbols, which is a very simple tool that we use in chemistry, especially when it comes to atoms. Now, what I'm about to talk about with respect to Lewis symbols only applies to elements that are in the A group, right? So we're talking about the representative elements in groups 1A, 2A, all the way to 8A, all right? And the concept behind Lewis symbol is very simple. Basically, the Lewis symbol of an element would be the symbol for the element, which would be, of course, what we're familiar with from before, Li for lithium, for example, C for carbon, and so on. And then around that symbol, we use dots to represent the valence electrons. So each dot represents a valence electron. So in the case of lithium, as you can see on the screen, lithium has only one dot. So therefore, that tells you that lithium has only one valence electron. Beryllium has two dots because it has two valence electrons, and so on and so forth. And of course, we can easily determine that because all we have to do is look at the group numbers of the different elements, and that will tell us the number of valence electrons, right? So for elements in group 1A, they all have one electron in their valence shell, so therefore the Lewis symbol will contain one dot. Elements in group 5A will have 5 electrons in their valence shell, and therefore the Lewis symbols of those elements will have 5 dots, and so on and so forth, right? So it's a very simple idea and very convenient, especially when it's used to show how bonds are formed, all right? So that's basically what the Lewis symbol is all about. Now, there's a statement here which, to be perfectly honest, is not always true. It says here that use the rules of electron configurations when forming dot structures or Lewis structures. For example, electrons remain unpaired if possible. To be perfectly honest, I've seen in some textbooks where the dots are not paired, right? So it's not really a big deal. So you can have the dots paired up or not, right? It doesn't make a difference. The representation is still the same, all right? So that's just something that I thought I should mention. Okay, so now that we have learned about Lewis symbols, we can understand how ionic bonds are formed. So remember we said that ions are formed as a result of atoms losing or gaining electrons. So if we look at the formation of sodium chloride, which I mentioned earlier, right? In the case of sodium, sodium has one electron on its outer shell, and therefore sodium will lose that one electron to form the sodium ion. At the same time, the chlorine atom will actually gain one electron to form the chloride ion, okay? And you'll notice that the chloride ion will have 8 electrons on its outer shell. And what is not clear here, but it is true, that the sodium ion will also have 8 electrons on its outer shell. In fact, it will have the same electronic configuration as neon, all right? So basically, as a result of the electron being lost here from the sodium and transferred to the chloride, you're going to end up with the sodium ion being formed and the chloride ion being formed, right? As a result, there will be a very strong attraction because now we have ions of opposite charges present in close proximity to each other. These charges are very strong, right? And therefore you end up with the compound being formed, sodium chloride. And because the force of attraction between them is so strong, this imparts certain properties to these compounds. For example, ionic compounds like sodium chloride have very high melting points, all right? They also have very high boiling points. They tend to be hard, all right? And what else? And they do not conduct electricity in the solid state. And that's because the ions are basically in a rigid state, right? They're very arranged in fixed positions with respect to each other. So these are the properties associated with ionic compounds, and it comes directly from the fact that these ionic compounds have ions which are strongly attracted to each other because they have opposite charges, all right? Now, so this is basically, again, showing you what happens. The electron is being transferred from the sodium to the chlorine atom, and you end up with your ion pair. And as I said before, the result of the strong attraction here is that the ions will be in a highly ordered arrangement, which is called an ionic crystal, all right? And this is, again, true for ionic compounds, generally speaking, okay? Here are some other examples of ionic compounds. And the point being stressed here is that the stoichiometry is important. In other words, the ratio between the ions is a fixed number for an ionic compound. So in the first example, you have the combination of magnesium with oxygen. Magnesium has 2 valence electrons. Oxygen needs 2 valence electrons in order to get its octet satisfied. So you're going to have the 2 electrons from the magnesium being transferred to the oxygen, and you end up with your magnesium ions and oxide ions. And again, you'll have a strong force of attraction between those ions. This one is a bit different because you'll notice that in the case of lithium, each lithium atom has only 1 electron. Now, oxygen needs 2, which means that there's a need for another lithium atom with its electron to be transferred to the oxygen. So we have this electron and this electron transferred to this oxygen. We end up with our ions, and we end up with your lithium ions on this side, 2 of them, and we end up with your oxide ion on this side here. So basically, in the case of the magnesium oxide, let me do this here. In the case of the magnesium oxide, the formula now becomes MgO, and in the case of lithium oxide, it is Li2O, indicating the ratio of the ions present in these compounds. Okay, so that shows you how ions are formed from the combination of metals and non-metallic atoms, all right? So this is what we were talking about with respect to how ionic compounds assemble themselves to form a ordered structure, which is called an ionic crystal. And what you'll find is that what is common among these compounds is that you can identify a segment of the structure, which is called a unit cell. And if you examine the gross structure carefully, you'll see that that unit cell repeats itself over and over again, all right? And this is typically what you'd find in any ionic compound, all right? So that's what happens in this case, which is the case of sodium chloride. Go back to my pointer. So this is the part of the structure of sodium chloride. And unfortunately, I don't have the unit cells shown here, I think. Hold on, let me check this here. Right, I don't have the unit cell here. We'll discuss more about unit cells later on. But once you identify the unit cell, you see that it repeats itself right throughout the structure. Going in any direction, either left to right, up or down, you see that the unit cell repeats itself, all right? One important thing I want to mention here before I leave this, this particular slide is that it's very important that you recognize that when it comes to ionic compounds, as you can see here in this structure, they don't exist as discrete units, all right? So what that means basically is that you'll never identify a molecule of, let's say, sodium chloride, because sodium chloride does not exist as a molecule, all right? A molecule is basically a collection of atoms that are held together by covalent bonds. But in the case of ionic compounds, you don't have that. You have what I described here earlier as a crystal structure, all right? So there's no such thing as a molecule of sodium chloride. So the formula for sodium chloride that we're all familiar with, which is NaCl, is not the molecular formula of sodium chloride, all right? In fact, this would be the empirical formula, because what this gives you is the ratio of sodium ions to chloride ions. But you can call this also the chemical formula as well. So the chemical formula for sodium chloride is NaCl, but you have to remember that it's not, this is formula, you have to remember that it's not a molecular formula, because of course there are no molecules of sodium chloride that exist, and that is true for every ionic compound. Okay, so so much for that. So the next we're going to talk about are the energy changes that will take place when you have a metal combining with a nonmetal to form an ionic compound, all right? And it is not as simple as just sodium plus NaCl. I'm sorry, it's not as simple as Na plus Cl to give you NaCl, all right? There are several steps that are involved, and with each step, you have your energy changes, right? So as stated here, the enthalpy of formation of an ionic compound is more important than the first ionization energy and electron affinity. We're going to talk about all of this shortly. In fact, the sum of the enthalpy change values for the individual steps is in accordance to Hess's law, right? And if you remember when we talked about Hess's law, I think this was in chapter 6, Hess's law basically says that the sum of the enthalpy changes for a reaction is independent of how you get from the reactants to the products, or independent of the number of steps that takes place as you go from the reactants to the products, right? So we're going to look at the energy changes that takes place in this kind of situation. And what will become important in examining this process is a tool known as the Born-Haber cycle, right? Which is used to calculate the overall enthalpy change involved in the formation of an ionic compound. And it is actually an application of Hess's law, all right? So the next slide I'm going to show you here is an example of the Born-Haber cycle applied to the formation of sodium chloride. So we're going to start off with sodium and chlorine here, right? Sodium, of course, is a solid and chlorine is a gas, all right? So basically sodium plus chlorine gives you sodium chloride, right? So the enthalpy change going directly from here to here is the enthalpy of formation of sodium chloride, solid, which is equal to minus 411 kilojoules, all right? Now, as I said before, this reaction here doesn't take place in one step. In fact, what you're going to see here is that there are several steps involved, starting from here, going this way, all right, and then coming down, all right? So I'm going to describe exactly what is happening at each step. And in fact, what I'm going to do is, I wish I could have done a split screen kind of thing. Okay, let me just work with this, all right? I'll try my best to explain what's happening here. Okay, so the first step in this process is where the sodium solid is converted to the sodium gas, all right? So the term for that is sublimation, right? Sublimation is when you have a solid converted directly to a gaseous state without going through the liquid state, right? So the enthalpy change, let me get my pen here. The enthalpy change here, for one, let me put that here. delta H 41 is equal to delta H sublimation for sodium solid, all right? And that is equal to, according to the information here, plus 107 kilojoules, right? And of course, it should come as no surprise that the enthalpy change is positive because heat is required in order for the solid to be converted to a gas. In other words, it's an endothermic process, all right? So that's what happens in the first step here, right? Now in the second step, what you have here is that the chlorine molecule is converted to chlorine gaseous atoms, right? And we call that enthalpy of atomization of chlorine. So delta H 2 is equal to delta H of atomization, ATOM, of Cl2, which in this case would be 122 kilojoules, all right? Now, in fact, to be perfectly honest, this would be actually 2 times 122 kilojoules per mole because the enthalpy of atomization here is for 1 mole of chlorine. But because you have a half mole here, then the enthalpy change here would be half of 2 times 122, which is 122 kilojoules per mole, all right? So that would be the enthalpy of atomization of chlorine. Okay, so now at this stage, we have sodium in the form of gaseous atoms and chlorine in the form of gaseous atoms. So the next step is the transfer of electrons from the sodium to the chlorine gaseous atoms. So we're going to do this in 2 steps. The first step is the energy required to remove an electron from the sodium atom, and that would be the ionization energy. So delta H3 would be equal to the ionization energy of sodium gas, which also would be endothermic, which in this case, according to the information provided, would be plus 496 kilojoules, 6 kilojoules, all right? So that would be the ionization energy of sodium, which is represented by this number right here, all right? So that's the energy required to remove an electron from sodium atom to form sodium gaseous ions, all right? So this is the electron being lost here by the sodium atom. And then now we get to the next step where the chlorine atom acquires the electron here to form the chloride ion, right? And that would be the electron affinity. If you remember the definition of electron affinity, okay, where's my pointer? Okay, if you remember the definition of electron affinity, it is the energy change taking place when an atom, which is gaseous, gain an electron to form a gaseous ion. So the electron affinity of Cl gas would be the same thing as delta H4 in this case, and that would be equal to, in this case, minus 394 kilojoules. Now you'll notice that it's negative, which means that energy is lost, which happens in every case where you measure the electron affinity of any particular atom. So therefore, this process is exothermic. And then the next step is a final step where you have the combination of the sodium and the chloride ions to form the sodium chloride, right? Now, going from here to here, energy will be lost, right? Now, let me explain something here. I'm kind of hesitating a bit because this might be a bit confusing. So let me try to be as plain as possible. So there's a concept or quantity known as the lattice energy, right, of an ionic compound, lattice energy, right? Now, again, this is one of those situations where if you look in different textbooks, you'll see different definitions, right? In some textbooks, the lattice energy would be, in fact, let me get out of this here for a minute and go to my, let me create another slide so I can write on this here. Okay. Okay. In some textbooks, if you have an ionic compound Mx, right, which is a solid, the energy required to break it up to form its ions, M plus gas plus X minus gas, right? The energy required to break this up is called, in some textbooks, the lattice energy, delta H lat, all right? In other textbooks, it's the other way around. Mg plus gas plus X minus gas gives Mx, all right? Now, in your textbook, if I'm not mistaken, the latter one is the definition that is used in your textbook, all right? So what we're going to do is, in fact, actually, I think it's the first one. Let me confirm that. Let me get out of this here and see if I can find it quickly. Let me go here. And let me go to files. I should have checked this out earlier because I know this document will take forever to download. But I think, if I remember correctly, going back to the PowerPoint here, or let me go back to this and download it in the meantime. Oh, it's going to take forever. Anyway, if I'm not mistaken, the definition in your textbook for the lattice energy is the energy required to break up this ionic compound into its constituent ions in the gaseous state. All right, so let's go with that. I'm going to confirm that later on, but for now, let's go with that, right? So in this case, the lattice energy would be, get into the full screen mode. In this case, the lattice energy would be the energy requiring the breakup of this into the ions here, all right? So basically, we're talking about for the reaction going in that direction and not in the direction shown by this arrow, all right? Okay, so basically, now that we have completed the Born-Haber cycle diagram, then basically we can establish the quantitative relationship between these different terms. And basically it comes down to this. The enthalpy of formation of sodium chloride would be equal to this, plus this, plus this value, and plus this value here, all right? Now, as I said before, the lattice energy would be for the reaction going in this direction. So in this case, delta H lat would be equal to plus 787 kilojoules, right? But in this case here, we're looking at it's going in the opposite direction like this. So basically, let me see here. Yeah, so basically that's how you establish the quantitative relationship between these different terms. Now, the reason why this is important is because it turns out that the stability of an ionic compound is dependent on the magnitude of this, right? The greater the magnitude of this value, the lattice energy, then basically the greater the stability of the compound. So therefore, it turns out that the lattice energy is kind of more important than the enthalpy of formation in terms of predicting the stability of the ionic compound, all right? Okay, so that's basically the Brown-Haber cycle. Let me go back to see if my textbook has been completely downloaded yet. Okay. Let me see here. I just want to make sure I'm confirming what I stated earlier so that, okay, so let me check the table of contents here. Okay, and let me look for Born-Haber cycle. Let me see, chapter 7 in this textbook. It would be the equivalent chapter. Let me see. Let me see. Sorry for this, folks. I should have checked this out before I started today's class. Okay, let me see. Lewis symbols. We talked about that already. Born-Haber cycle. Where are you? Oh, come on, come on, come on. Okay, I think we are there. Okay, so I was correct. The lattice energy is the energy required to break up the solid into its constituent ions, right? So that's a definition we're going to go with. All right. As I said before, there are some textbooks which says the lattice energy is the opposite, right? So to avoid any possible confusion, we're going to go with this definition that you see. In fact, the definition is given in words right here. The lattice energy of an ionic compound is defined as the energy required to separate 1 mole of a solid into its component gaseous ions. All right, so that's a definition that we will be going with for our purposes in this chapter. All right. Okay. Any questions about the Born-Haber cycle? Any questions?
No, I don't think so. Oh, wait, if the lattice energy is negative, going from
no.
Yeah,
It's
no.
According to the
in this
definition that we just mentioned, right?
Yeah,
the lattice energy is going to be positive.
Yeah, but in this example, it's loose energy forming the solid compound. Would that be the energy? It would be the energy required to assemble it into an ordered structure.
Right, exactly. That's the opposite direction, right, exactly. And as I said before, some textbooks actually define it that way. But in our textbook, it's the opposite direction. So that's what we're going to go with. All right?
I see. All right.
And I thought it's important to mention that because, you may, some of you may look in other textbooks or look in other internet sites and see the opposite definition. So I don't want to confuse you guys about that. So we're just going to stick to the definition as it is in your text. All right? Okay. So that's the Born-Haber cycle. Okay. Let me skip this. Okay. So now we're going to get into covalent structures. What time is it, by the way? It's 1:10. Okay. Very good. So we're going to get into covalent structures, molecules, and we're going to apply what we learned concerning Lewis symbols to structures, to molecular structures. All right. So the simplest molecule, of course, is the hydrogen molecule, consisting of 2 electrons being shared between the 2 hydrogen atoms. So this is what you see here on the screen. Here you have one Lewis symbol for hydrogen. Here you have another Lewis symbol for hydrogen. When they come together, they share those 2 electrons between them, and you end up with the Lewis symbol for the hydrogen molecule. All right. So this is the Lewis symbol for the hydrogen molecule. There's also another representation that is more often used, where the paired electrons is represented as a dash or a line. So you can also use this representation here as the Lewis symbol or the Lewis structure for the hydrogen molecule, all right? Where this line represents a pair of electrons, all right? So that's the Lewis symbol for the hydrogen molecule. But of course, there are more complex molecules than hydrogen, so we're going to apply this concept to such molecules, right? But before we get to that, let's look at the statement here. Very important for you to recognize that the Lewis structure shows you basically which electrons are involved in bonding. And when that happens, the atom or all the atoms try to obtain the noble gas configuration. In other words, they try to obey the octet rule. And the reason why I say try to is because, as you're going to see later on, in some cases, that is not possible, right? But we're going to get into those exceptions shortly. So basically, what this is, the point being made here is that for each hydrogen atom in this structure, they end up with the group 8 configuration. Now, of course, in the case of hydrogen, it's not 8 electrons being shared between them, but 2 electrons, right? So therefore, each hydrogen atom has 2 electrons on its outer shell, which has which is the same as the electronic configuration of the nearest group 8 element, which would be helium, all right? So in that case, the duet is satisfied, all right? Okay, so going along to more complex structures, firstly, we have to make some distinction between what we call the bonding pairs of electrons and the non-bonding pairs of electrons, right? So the bonding pairs of electrons are those electrons which are shared, those pairs of electrons which are shared between the atoms in a molecule, right? And as I said before, you can use a dash to represent that bonding pair. So here's another example. This dash here represents a pair of electrons shared between the hydrogen atom and the chlorine atom in the molecule of hydrogen chloride. Here is another example. So in this case here, we have the Lewis structure for chlorine. And as you can see, you have 2 electrons being shared between the chlorine atoms, but each chlorine atom has some other pairs of electrons surrounding it, 2, 4, 6 pairs of electrons for each chlorine, which are not involved in bonding. And we call those non-bonding pairs of electrons lone pairs. So we can use the term non-bonding pairs or lone pairs to describe the electron pairs that are not involved in bonding in these molecular structures. And again, oh, I'm sorry, yes, sir.
I thought that hydrogen chloride was a ionic compound. No?
No, hydrogen chloride is a molecule. Now,
okay,
if you dissolve it in water, then it converts to an ionic compound. In fact, an ionic solution, let's put it that way, in water. It separates into H+ ions and chloride ions. But the gas itself, the hydrogen chloride gas, before you dissolve it in water, is actually a molecular compound.
I see. Right? Well, that's interesting.
So in the gaseous state, it's molecular, but when you dissolve it in water, it immediately dissociates to form the hydrogen ions and the chloride ions. All right. Okay, another thing I want to mention here, which is not mentioned in the slides here. You can also use lines to represent the bonding pairs. In other words, let me go back to my pen function here. And let me put it somewhere up here. In the case of chlorine, you can represent it as Cl bonded to Cl. And then you have lines here, 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 whoops, here, and here for the lone pairs. But you can use this representation as well when it comes to drawing the Lewis structures, showing the bonding pairs and lone pairs as lines, all right? Key thing you need to remember, if you're using this representation, is that each line represents a pair of electrons. Excuse me, each line represents a pair of electrons, right? That's very important because sometimes students, confuse a line representing an electron, but each line represents a pair of electrons, all right? Okay, so those are some simple examples. And here are some other examples of Lewis structures representing different molecules. Now, this is a series of compounds of non-metallic elements bonded to hydrogens from period 2, all right? So we're starting with carbon here, bonded to 4 hydrogen atoms, right? That's a Lewis symbol for this molecule, which is known as methane. And then we have this one here, which has nitrogen bonded to 3 hydrogen atoms. And you'll notice that there's a lone pair of electrons here on the nitrogen atom. So that's the structure of ammonia. And then the next in this series, you have water, which has 2 bonding pairs and 2 lone pairs around the oxygen. And then finally, in the case of hydrogen fluoride, you have 1 bonding pair and 3 lone pairs of electrons around the fluorine. So you see that there's a trend that one can observe as you go from one compound to the next in the series. The number of lone pairs increases and the number of bonding pairs decreases, but the total number of pairs of electrons around the central atom is the same, which is 4 in each case, all right? So that's basically the trend that we'll observe when it comes to this series of compounds, all right? Okay, some other things we need to talk about when it comes to the formation of covalent compounds. Now, in some cases, what you'll find is that when a bond is formed, a covalent bond that is, it is formed as a result of both pairs of electrons coming from one atom, all right? We call that bond a coordinate covalent bond. back in the dark ages when I was a student, the other alternative term, I haven't seen it much lately. They call it a dative bond in those days when I was a little scrub coming up. So if you happen to come across that term, it's the same thing as the coordinate covalent bond, all right? Okay, so here's an example. If you add any acidic substance providing H+ ions to ammonia, then what will happen is that both of these electrons will be donated to the hydrogen ion, all right? And the result will be this. Let me do this down here. So the result would be H bonded to N, bonded to H, bonded to H. You have the lone pairs here, and then you have the H+ here. So what's going to happen is that this pair of electrons will be donated to the hydrogen ion, and you're going to end up with H, N, H, H, and H. You're going to have a plus charge here. And this bond here will be the coordinate covalent bond. All right. So there are some instances where that will happen, where both pairs of electrons will come from one atom, donated to another atom, and the bond that is formed as a result would be the coordinate covalent bond, right? It's still a covalent bond, but it's different because both electrons are coming from one atom. Okay, so that's just a little thing I need to discuss with you, coordinate covalent bonds, all right? Now, another thing I need to mention is the fact that you can have a situation where you have more than a pair of electrons being shared between two atoms, right? And this brings into focus certain terms, namely double bonds and triple bonds, right? Now, going back to the hydrogen chloride example, we have one pair of electrons being shared between the hydrogen and chlorine, so we call that a single bond. However, in some molecules, such as in the case of carbon dioxide, you'll notice that, for example, between this carbon and this oxygen, you have two lines, which means that you have two pair of electrons being shared between them, right? So what that means basically is that, according to the terminology that we're using now, we call this a double bond, right? A double bond is basically two pairs of electrons being shared between two atoms, right? So in the case of the carbon dioxide molecule, we have a double bond here and we have a double bond here, right? And then we have what are known as a triple bond, where you have three pairs of electrons being shared between two atoms, such as in the case of the nitrogen molecule, right? So that's a triple bond. And believe it or not, there's actually a fourth type of bond known as a quadruple bond, but we won't be concerned with that in this particular chapter. That's a bit beyond the scope of our discussion in this course, all right? So for our purposes, we'll be concerned with only single, double, and triple bonds in our molecules, in our Lewis structures. Okay, so now we're going to get into how do we write down Lewis structures, right? So basically, if you're given a formula for a molecule or a polyatomic ion, how would you determine the Lewis structure of that molecule? And in order for us to do that, we have to go through some steps. But I'm going to give you just some general information here to begin with. First thing you need to recognize is that wherever you have hydrogen atoms present in a molecule, wherever you have hydrogen atoms present in a molecule, then those hydrogen atoms must be terminal. In other words, these hydrogen atoms can only be bonded to one atom, right? So you won't have a situation where a hydrogen atom is bonded to one atom and then bonded to another atom simultaneously. And the reason for that is simple. Hydrogen can only have in its outermost shell 2 electrons as a maximum number of electrons in its valence shell. So therefore, it can only form one bond with other atoms. All right. So as you can see here in the case of this molecule, in each of these cases where you have hydrogen atoms, they're all each bonded to just one atom and can't be bonded to any other atom. All right. So that's the first thing I want to mention here. The next thing I want to mention is that usually when it comes to determining the Lewis structure of a molecule, we have to determine which atom will occupy the center, right? Usually, what you'll find is that the atom that will occupy the center position or the middle position in the structure is the atom with the lowest electronegativity value, all right? I think we talked about electronegativity earlier, and even if I haven't, you should have met this concept in introductory chemistry. But just to briefly tell you what electronegativity is, it is basically the attraction that an atom will have for sharing electrons, right? So when you have an atom sharing electrons with other atoms, in some cases where the atoms are different, one atom will have a stronger attraction for the other. And there is a scale that has been developed by a scientist by the name of Linus Pauling, where he determined, it's a 4-point scale, and based on the scale, and based on the numbers associated or assigned to different elements, one can determine which element is more electronegative than the other. In fact, I'm going to show you where that table is in Canvas. So let me get out of this here. Let me go back to your course in Canvas. Let me get out of this here. And let me go to tables and tables chemistry. Download. Okay, and let me scroll down. Okay, so this here is the table I'm referring to, right? It gives you the electronegativity values of different elements, right? And as I said, it's a 4-point scale. Fluorine is the most electronegative element in the periodic table. So you will never find fluorine at the middle of a structure, a Lewis structure. All right, so this is what you're going to use to determine which element should go to the middle, right? The element with the lowest electronegative value of the elements involved in the structure will be the one that you'll place in the middle. So for example, in this arrangement that we see here, carbon has the lowest electronegativity value of these other elements, 2.5, whereas the chlorines have a value of 3.0 each, and the oxygen is 3.5. So therefore, when it comes to arranging them in a skeletal way, the carbon will be in the middle, and then you'll bond it to the surrounding chlorine and oxygen atoms, all right? Okay, so that's another thing that you have to keep in mind when you're drawing the Lewis structures of molecules or polyatomic ions. When it comes to oxyacids, like sulfuric, nitric, and so on, the hydrogen atoms are usually bonded to the oxygen atoms. So again, when it comes to arranging the atoms in a skeletal way, in the case of sulfuric acid, this would be the arrangement. The sulfur in the middle, the sulfur is bonded to the oxygens, and then the hydrogens are bonded to the oxygens, right? So that's typically how the arrangement would be in the case of oxyacids. And another thing I need to mention here is that when you're putting together the skeletal arrangement of the molecule, try to have them in a compact fashion. So for example, in the case of SO2F2, this molecule, I would put the sulfur in the middle and surround it with the other elements and don't have them in a linear fashion, as you can see here, all right? The more compact structure is usually the correct arrangement, all right? Okay, what next? Okay, so as I said before, there are some steps involved in drawing the Lewis structure of a molecule, all right? And the steps are outlined here, even though, in my opinion, this does not adequately describe what you should do. So I'm going to actually show you how to do this, basically by doing a couple of examples, right? But let me just go through the steps indicated here. So the first step is that you determine the total number of valence electrons, right? And we all know how to do that. All you have to do is go to the periodic table, look up the group number, add them up according to the formula, and that gives you the total number of valence electrons. Then it says, write a plausible skeletal structure and connect the atoms by single bonds or single dashes, right? So if you remember what I said before in the previous couple of slides, one, you have to make sure that the least electronegative element is placed in the middle, and then you place the other atoms around it. You try to make it as compact as possible. If there are any acids that are oxyacids, make sure that you have oxygens bonded to hydrogens. and so on and so forth. Then it says, place pairs of electrons as lone pairs around the terminal atoms to give each terminal atom an octet. But of course, hydrogen would be the exception because hydrogen cannot have more than 2 electrons on its outer shell, right? And then it says, assign any remaining electrons as lone pairs around the central atom. And then it says in the next step, if necessary, move 1 or more lone pairs of electrons from a terminal atom to form a multiple bond to the central atom. So these are the general steps involved. And as I said before, we're going to do a couple of examples so that you can see how these steps actually work. And also the fact that there's some other steps involved along with the steps that are outlined here. And I'm going to get into that when we actually do the examples, all right? Okay, but before we get into these examples, there's one important concept that I need to introduce to you, which I'm quite sure you never learned in your introductory or high school chemistry. And this is the concept of formal charge, right? And again, this is a situation where if you look in different textbooks, you'll see different worded definitions, which basically means the same thing, right? So here's a definition that I have here on the screen. The formal charge of an atom, I probably should have put there, is the difference between the number of valence electrons in a free uncombined atom and the number of electrons assigned to that atom when bonded to other atoms in a Lewis structure, all right? Now, to simplify this, I'm going to give you a formula that you can use to determine the formal charge of an atom. And the formula is simply, hold on, let me see here. Okay, so let me squeeze the formula up here. So the formal charge of an atom is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons, all right? So that's the formula that you're going to use to calculate the formal charge of any atom in any Lewis symbol, Lewis structure for a molecule or polyatomic ion. And this will become important when it comes to determining the Lewis symbol, right? So, so what I'm going to do, since I have this example right here, I'm going to show you how to use this formula to calculate the formal charge of the sulfur atom here and the formal charge of the carbon atom here, all right? So, okay, let me not try to squeeze this in the space. I'm just going to create another slide. What am I doing? New slide. Okay. So in the case of carbon disulfide, the Lewis structure is C double bond S with 2 lone pairs here, and double bond S on the other side with a lone pair here and here, all right? So the formal charge for the carbon, now remember, let me write the formula up here just to remind you. The formal charge is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons, all right? So in the case of carbon, the group number, if you go to the periodic table, you see that the group number is 4 minus half the number of bonding electrons. Now for the carbon here, you have a total of 2, 4, 6, 8 electrons, so half of 8, right? And then for the non-bonding electrons, the carbon has 0 non-bonding electrons, so this will be equal to 0. So the formal charge on the carbon here will be 0, it has no charge. And then for the sulfur here, the formal charge on the sulfur is equal to, it's equal to the group number, which is for sulfur 6, you get that from the periodic table, minus half the number of bonding electrons. Now for each sulfur, the number of bonding electrons here is 2 plus 2, 4. So half of 4 minus the number of non-bonding electrons, which for each sulfur is 2 plus 2, which is 4. And if you work this out, you're going to see that this is 0. So therefore, there's no charge on any atom within this molecule, all right? So that's basically how you use this formula right here. It is the group number minus half the number of bonding electrons minus the number of non-bonding electrons. As I said before, this formula will become very important when it comes to determining the Lewis structure of certain molecules, all right? Any questions about this? Any questions?
Yes. The bonding electrons, is that including the electrons bonded to other atoms?
Yes, exactly. So in the case of carbon, let me show you this here. Shucks.
Carbon's got 4 valence electrons, right?
Yeah, but in this case here, let me get to my pointer so you can see this clearly. In this case here, this carbon has 4 electrons sharing with this sulfur and 4 electrons sharing with that sulfur, right? So therefore, the total number of bonding electrons is 8 for the carbon, right?
But if we're using this to determine what the Lewis structure is like, wouldn't we need to know that it has 8 bonding electrons for that to work?
Right. Well, yeah, but we're going to get to that later on. I think what you're talking about is how do we get the Lewis structure in the first place, right?
Yes.
Right.
I thought that this formula is for that.
Right. Well, this is the formula that I'm using as an example. Later on, I'm not sure if we're going to get, in fact, we'll probably do some examples shortly, but later on, you're going to see how we determine the Lewis structures, right? It's a step-by-step process. But what I'm just showing you now is just how to determine the formal charge if you have the Lewis structure. You see what I'm saying? So we're going to look at...
That makes sense.
Yeah, so we're going to look at how we determine the Lewis structure, shortly, all right? Okay,
All right, cool.
Any other questions concerning formal charge calculations? Any other questions? Okay, so let me just skip this here. I think I discussed this before, or maybe I didn't. Let me see here. Usually the most plausible. Okay, actually, let me go through this. It says here, usually the most plausible Lewis structure is the one with no formal charges, right? Now, in some cases, what you'll find is that there are some structures where you'll end up with a net charge. In other words, what you'll see is that there are some negative charges present close to plus charges. The negative charges will cancel out as many plus charges. But what you'll find is that in some cases, there might be an excess of plus charges or an excess of negative charges, right? Which I think is what the next line is talking about. It says, when formal charges are required, they should be as small as possible, and the negative formal charges should appear on the most electronegative atoms. So that is not what I was talking about, but nonetheless very important. So what this is saying is that when formal charges are required, we try to cancel out the charges such that you have few charges, and if any negative charge is present, they must be on the most electronegative atoms. Atoms that are adjacent in structure should not carry formal charges of the same sign. So these are just some general points to be made when it comes to determining the Lewis structure of a molecule or a polyatomic ion. Some other things we need to talk about. There are some situations where a Lewis structure would result in atoms that don't have 8 electrons on its outer shell, such as this example right here. So if you look at this structure here, which is the Lewis structure for nitrogen dioxide, you'll notice that the nitrogen here has a single electron, right? And that's basically how it ends up because we don't have enough electrons in this structure to ensure that each electron is paired up, right? So there's a special name given to structures like these, where these are called free radicals, right? Free radicals are basically structures where you have at least one unpaired electrons. And free radicals are typically unstable. They tend to combine with almost anything in order to gain that extra electron, because in the case of nitrogen, you'll notice that it does not have an octet. It has a total of 2, 4, 6, and then 7 electrons. So therefore, what will happen is that this molecule would readily react with something in order to gain that extra electron so that the nitrogen will have its octet satisfied, all right? So that's one situation where you have atoms in a molecule that does not obey the octet rule, all right? Here's another situation here where in the case of boron trifluoride, you'll notice that the boron here does not have an octet, 2, 4, 6, right? So what would happen in this case is that a pair of electrons, let me get to my pen here, a pair of electrons from one of the fluorine atoms here will be donated here to form a more stable structure, right? So you're going to end up with this structure right here, which is a more stable structure because now the boron has 2, 4, 6, 8. In other words, the boron now has an octet satisfied, all right? And this is typically what you see in compounds of beryllium, boron, and in some cases aluminum, all right? So that's what happens in this case. You can have a situation where there are some atoms which can have more than 8 electrons on its outer shell. And these are 2 examples being shown here. In the case of the first one, phosphorus pentachloride, the phosphorus here will have 2, 4, 6, 8, 10 electrons on its outer shell. And the sulfur here will have 2, 4, 6, 8, 10, 12 electrons on its outer shell. And we say that atoms of this type can expand their octet. That's a term that they use in chemistry, where instead of just having 8 electrons on their outer shell, they can have more than 8 electrons on their outer shells, right? And this is observed specifically for elements belonging to periods 3 and below. So periods 3, 4, 5, and below that, 6, 7, can have more than 8 electrons on their outer shell. Elements in periods 1 and 2 simply cannot do that. And there is a reason for that, which we will get into in the next chapter. We won't be able to explain that in this chapter. We'll get into that discussion in the next chapter. But this is also another important point that you need to understand and recognize when it comes to Lewis symbols or Lewis structures for compounds containing elements in the central atom, which belongs to periods 3 and beyond. All right. Okay, so that's that. And this is also another example where you can have an expanded valence shell where more than 8 electrons are present, which could include a lone pair of electrons, which is what we have here in the case of boron pentafluoride, all right? I'm sorry, bromine pentafluoride. Okay, so that's another example of the expansion of the octet in certain molecules where the central atom can have more than 8 electrons on its outer shell. Okay, so electronegativity, what time is it? Let me see here. It's now 1:40. You know what? I think I'm going to stop here. Let me just check something out here. Okay, yeah, I'm going to stop here for today. But before you leave, you may have seen the announcement I made. I think I posted it on Sunday evening, that your next test is actually due this week, but what I've decided to do is put it off until next week, all right? So I'm going to let you know, I'm going to post another announcement, letting you know what chapters will be covered for test number 2. And I'm also going to try to, as soon as possible, scan and upload the answer keys for the tests that covers the topics that will be on the test that you'll be doing for test number 2. I'm also going to email you guys your individual graded work so that you have that as well to review, all right? So that is all in preparation for your test next week. So let me take roll and let me take roll, and then if you have any questions, let me
this is just a note, but I resubmitted quiz number 8 because I didn't fully write down all of my significant figures. Like,
oh, okay, yeah, no problem.
All right, cool.
Yeah, no problem. So today is the today is the 13th. Okay, so let me stop sharing. Okay, so let's see who is here. Arias Rios, not here. Barber
Here.
is here. Cannon, not here. Chang, not here. Chavis, not here. Clark, not here. DeGraff, not here. Franklin, not here. Han, not here. Hannick, I don't see Hannick. Holland, I see Holland.
I'm here.
Yep. Jurgensen, I don't see Jurgensen. Reese, I don't see Reese. Rouse is here.
I'm here.
Yep. Runnels is here. Santiago is here. And Smith, I don't see Smith. Okay, so any questions? Any general questions? You have 2 minutes. Any general questions, problems? If not,
I'm good.
that's it for today. So enjoy the rest of your evening, and I'll see you guys on Thursday. All right, so take care.
All right, take care.
Adios.